Hello, welcome to S Chemistry. I'm your instructor Dr. Suhas Gaudi and I will be teaching BSc 5th semester Physical Chemistry course on colligative properties of dilute solution. Here is the outline. So in this class I am going to cover the application of depression of freezing point, which is we can calculate or determine the molecular weight of the solid in the given solution, followed by the Bachmann methods to calculate or to measure the depression of freezing point. So it's a apparatus. So let's start with the first point, that is determination of molecular weight from depression of freezing point. So from the previous class we are continuing the equation 1. So where delta T is directly proportional to the P minus Ps, that is lowering of vapor pressure. So here delta T represents the depression of freezing point. Temperature difference between pure freezing point of pure solvent and freezing point of pure solution, difference between temperature, freezing point temperature, from that we get the this delta T, and P minus Ps, this is for pure solvent and this is for pure solution. We shows that vapor pressure, that is lowering of vapor pressure. Since P is constant for the same solvent at a fixed temperature, from equation 1 we can write that so delta T is directly proportional to the P minus Ps divided by P. So here we get equation number 2. But from Raoult's law for dilute solution, the P minus Ps divided by P is equal to small w into m divided by capital W into small m. So this gives the equation number 3. Since capital M, that is molecular weight of the solvent, is constant from 3, that is P minus Ps divided by P is equal to small w divided by capital W into m, that become equation number 4. So if you equate this equation number 2 and 4, so here P minus Ps divided by P, this term that is lowering of vapor pressure is common in equation 2 and 4. So certainly you can equate delta T with this equation. So delta T is directly proportional to the small w into uh, divided by small m into 1 by capital W. So this is nothing but if you multiply with constant, you will get equation number 5, that is delta T is equal to Kf into W divided by small m into 1 by capital W. So this term represents the number of moles of the solid, and where small capital W is nothing but your weight of the solvent. So here where Kf is a constant called we call it freezing point constant or cryoscopic constant, or also we call is a molar depression constant. So what is mean by molar? So here molar means your number of solute, that is small w divided by m, it has to be number of mole has to be 1, and your it should be w means weight of the solvent should be 1. So in that case your delta T is equal to the Kf value. In that case we consider as a molar depression constant. So let us see what is meant by molar depression constant. So molar depression constant may be defined as the freezing point depression which is produced when 1 mole of solute is dissolved in 1 kg of the solvent. So in this case you can take as a, like for example, you can take like 1 mole of sodium chloride, that is salt, if you add into the 1 kg of solvent, that is water. If you add, you will get the 1 molar solution, and if you calculate the freezing point for the solution, you will get the molar depression constant. So at that time you will get this equation number 5. So where delta T is equal to Kf into w divided by small m into 1 by capital W. So here this term represents the number of moles of the solid, and this is like solvent. So if you multiply with the constant K, you will get the depression of freezing point. So if the here all masses are the given in the kg kilograms, but if you get the mass of the solvent in grams, then gram that has to be converted into kilograms. So equation 5 become it can change, uh, like you have to divide with the thousands of that solvent mass. So you will get the equation, this equation. So delta T is equal to Kf into this number of mole of the solute, that is small w divided by small m into 1000 divided by capital W. So if you take the small m, which is molar mass of the solute, to the right hand side to left hand side, and if you take this delta T to the right hand side as a denominator, so you will get the equation number 6. So in this equation, where small m represents the molecular mass of the solid, Kf represents the molar depression constant, small w represents the mass of the solute, that is in the grams, and delta T represents the depression of freezing point, and capital W represents the mass of the solvent, that is given in the grams. So in this way, if you put the value or parameter here, you will get the molecular mass of or molecular weight of the solid. Now for the given value of Kf, the molar mass of the solute can be calculated. So sometimes the value of Kf is given in Kelvin per 0.1 kg, that is 100 gram. In that case, the expression 6 become m equal to 100 into Kf into small w divided by delta T into capital W. So the value of Kf can be determined by measurement of delta T by taking a solute of a known molecular mass m, small m, in and the substituting the value in expression 6. So the constant Kf, which is characteristics of particular solvent, can also be calculated from the relation. So this relation comes from the thermodynamic equation. So Kf is equal to capital R into Tf, that is freezing point of solvent, square divided by 1000 into Lf. So where Tf represents the freezing point of the solvent in Kelvin, Lf represents the molar latent heat of fusion, where R represents the gas constant, that value is 8.32. So thus for water we can calculate the Kf value. So for water we know the freezing point, that is 0 degree Celsius or in Kelvin 273 Kelvin, and Lf for the latent heat of fusion is for water is 336 joule per gram. So 336 joule per gram. So if you put all this data in this equation, so you will get the final answer 1.86 Kelvin per kilogram. So that is the value of Kf. So now we will see the Bachmann methods. So Bachmann is a name of scientist who invented this instrument apparatus. The depression of freezing point can be measured using these Bachmann methods, so more correctly with a less difficulty. So as you can see in right hand side, you have this Bachmann apparatus. So here we see the relation between lowering of vapor pressure and the depression of freezing point. So now we will see the apparatus. So what are there? So apparatus consist of a freezing tube with a side arm, which is shown over in this figure. So here, so in this figure, so the use of this freezing tube is to contain the solvent or solution, while the solute can be introduced through the side arm. So this arm is used to just to add the solid into the this freezing tube. So next is a thermometer. Thermometer is to measure the temperature, and third is the cooling bath. So cooling bath is to cool the freezing point tube. So you have this freezing tube, so you can freeze using this cooling bath. So next is a freezing bath. So freezing bath is for accurate freezing point determination. So this is a freezing bath. So air jacket. So here between this tube, inner and outer, in between you have this air gap. So air gap is just to control and stabilize the temperature. And you have the solvent. The solvent is the substance whose freezing point is being determined, that is our area interest of compound, and the solute is a substance to be dissolved in the solvent. So these are the apparatus for the Bachmann method. Now we will see the procedure part, like how we are going to measure. So first we will take the initial freezing point. So in that case we will determine, like we will take 15 to 20 grams of the solvent and place it in the freezing point tube, followed by cool and the freezing point tube in the cooling bath, which ensure the thermometer bulb is fully immersed in the solvent. Then we will observe and record the approximate freezing point of the solvent. So this is only for the pure solvent. Now again we will melt that given solvent, and again we will refreezing. So once you have the approximate freezing point, and further we will melt the solvent by warming it up. Then we will place the freezing point tube back into the freezing bath. So we will allow the temperature to drop within about 1 degree Celsius of the approximate freezing point, which is previously determined. Then we will accurately measure the freezing point. Then we will dry the freezing point tube thoroughly to remove any condensation. Followed by, we will place the tube continuously in the air jacket, which helps to control the cooling rate. Since we have this air jacket, your cooling will be slowly and continuously, so you can actually control the cooling rate, which allow the temperature to fall slowly and stabilize to about 0.5 degrees Celsius below the approximate freezing point. Then we will stir the solution vigorously, so this will induce freezing and release the latent heat, which is causing the temperature to rise slightly. Then we will record the highest temperature reached at the freezing point of the solvent, and we will repeat the process for the accuracy, just to ensure the accuracy, and repeat the freezing point determination process to get the concurrent value or consistent value. So this is the part of the procedure. So then we will further add the solute part through the side arm. Once the accurate freezing point of the solvent is determined, again we will melt the solvent by warming it up. Then the weight a small amount of solute, that is 0.1 to 0.2 gram, and introduce it into the solvent through the side tube. This mixture thoroughly to dissolve the solute, and repeat the freezing point determination for the solution in the same manner as for the pure solvent. We will repeat the procedure as we did for the pure solvent. Then we will take the additional measurement if necessary. Then we will add more solute and just determine the freezing point of the new solution. So this will allow us for the determination of how the freezing point changes with vary amount of the solute. Then we will come to the calculation part. So knowing the depression of the freezing point, the molecular weight of the solute can be determined using the above given expression. So using this expression we can calculate from experiment we can calculate this delta T, then we will be knowing this capital W and small w, then easily we can calculate or find out the molecular weight of the solute. So there are some drawbacks, plus point is there. So this method gives accurate results if the following precautions are observed. So the supercooling should not be exceeded 0.5 degrees Celsius. That is the first precaution. Second precaution you have to take, the stirring should be uniform at the rate of about 1 movement per second, and the temperature of the cooling bath should not be 4 degree to 5 degree below the freezing point of the liquid. So cooling bath temperature is very much important in this case. So it should not be like below the freezing point of the liquid, like 4 degree to 5 degree at max. So that difference has to be maintained. So here are the references for the given lecture for the images, and for content you can follow these 3 books. Here we come to end of this lecture. So thank you for kind listening. See you in next lecture. Till then, happy learning.